Hello there and welcome to another tutorial. My name is Tanmay Bakshi and this time we're going to be going over how you can use CUDA for massively parallel array arithmetic. Now in this video today, I'll show you how you can actually implement CPU C code in order to take two arrays of constant length and of course the exact same length, say 5,000 elements in each array. Now we will be working with of course a lot more elements in this video, but just for example, what you could do is actually add, subtract, multiply, or divide each element in the array. For example, the first element in the first array and the first element in the second array could be added together or even multiplied or subtracted or divided, and that result would be the first element in the resulting array, the third array, which is the final return value. Now, after I show you how you can implement that in CPU code, I'll tell you a few of the drawbacks of converting this to parallel code, whether that be parallel CPU or GPU code. Once that's done, I'll show you how you can actually code in that very same system in CUDA C code to create a parallel GPU version of that massively parallel array arithmetic. But now let's get over to the Mac part where I'll show you how you can actually implement all of this code. Alright, so welcome back to the Mac part, and now I'm going to show you how you can actually implement all of this. Now let's get started with actually taking a look at a CPU implementation of such an application. Now as you can see, this is a little bit of what the code looks like. It starts off with the includes, and of course with C we're going to be including the standard input and output and standard libraries. After that, I'm going to define a variable called size, and I'll talk about what that actually means in just a moment. After that, I'm going to declare the actual functions that will do the addition, multiplication, division, and subtraction. And in this case, these are called matrix add, matrix multiply, matrix divide, and matrix subtract. The inputs for these functions are input 1, input 2, the output, where the output will actually go, and of course the index of where exactly the input should be taken and the output should be given. After that, all they simply do is they actually take the output array, or a pointer to the output array, and they set the indexeth element to the input 1's indexeth element plus the input 2's indexeth element. Matrix add will then be called as many times as there are elements in the input 1 and input 2 arrays. It will put the results in the output array, and it will use index to find out which number of the function is actually being called to find out which element in the arrays to actually use and set. Very similar logic is actually set for the matrix multiply, divide, and subtract functions, except the fact that we're not adding, we're either multiplying, dividing, or subtracting, as you can see here. But after that, in the int main function, we're ready for the actual logic that'll allow us to run this code. Now, of course, it actually begins with allocating the input 1, input 2, and output arrays. The way we do this is by declaring a pointer to input 1, input 2, and out. Each one is equal to malloc, meaning memory alloc. The size we're passing it is the size variable we defined up in the top of the code, multiplied by the size of the float data type. And then we're converting this from a void pointer to a float pointer, and then putting that into in1, in2, and out, respectively. Now you've allocated all of your memory. Now you actually have to give these variables meaning, and once you give them meaning, you actually have to allow these variables to be given to the functions, and then once the functions have the variables, they will run their logic on them. The way you do this is by looping through 0 to the size variable that we defined at the top of the code. Now the iterator here is going to be an int called I, and the way you do this is by saying for int I is equal to 0, I is less than size plus I, meaning while I is less than size with an initial value of 0, increment I and then return its value. Or at least that's what this means over here. Now once that's done, then you're going to take the ith element of in1 and set it to the I variable. You're going to take the ith element of in2 and set it to the I variable. And you're going to take the ith element of the out variable and set it to 0. You'll then run the matrix multiply function on the in1 and in2 arrays, the out array, and of course the I iterator. After that, you're done running the matrix function. You can then printf the first 10 results and then loop through I 0 to 10, meaning 0 to 9 in this case because of the way that this is formed. And from there, you can actually print out all of the first 10 elements in the out array. Now, if you were to run GCC to compile this script and then actually run the file that GCC gives you out, you can see that the first 10 results are 0, 1, 4, 9, 16, 25, 36, 49, 64, and 81. And this makes sense because, of course, the first element is 0 times 0, then 1 times 1, 2 times 2, 3 times 3, 4 times 4. It continues and continues, 5, 6, 7, 8, until it's 9 times 9. And as you can see, that is correct. Now, of course, this is to be expected, because you're running this on the CPU, so any calculations you perform here will be extremely precise. However, when running it on the GPU, that's a little bit of a different story. Now let's talk about how you can convert all of this code to GPU code, which you can then go ahead and run and actually run this in very, very highly parallel fashion in order to get your results. Now, first of all, there are quite a few drawbacks when you're converting this to parallel code, whether it be CPU or GPU. The number one drawback is, well, first of all, this isn't very computationally expensive, meaning each operation doesn't take very much time. When each operation takes a lot of time, that's usually when you want to implement more parallel procedures. However, again, in this case, we're not necessarily looking for whatever takes more time because we're doing so many in parallel that the plain fact that doing millions in parallel, it adds up to give us a big time saving. However, apart from that, you also have to remember that when you do things in parallel, you also have to combine the results. If you've got 8 people doing work for you, you need to actually go ahead and take the results and combine them into one list of results. You can't just take the results and do nothing with them. You can't just have 8 separate lists of results. And so there's another sort of bottleneck when you're taking all the results and combining them back to be used in another sequential manner. And so those are just a few of the drawbacks. However, with GPUs, these drawbacks are even more amplified because, first of all, GPUs do individual operations much slower and much more computationally expensively than CPUs do. They also do them with much less precision than CPUs can do them. And of course, when you're using GPUs, you have an entirely different memory space than when you've got CPUs. What this means is that as you are using your GPU, you need to copy your input variables onto your GPU memory. And then, once you do the calculations in the GPU, you need to copy the output variables back onto CPU or host memory. Now, this is quite a bit of a bottleneck, and this can become one of the reasons that your application performs slower on GPU and faster on CPU. However, with extreme parallel operations, this cost is really nullified. The CPU in general will take more time to execute than the GPU would to copy onto the GPU, run, and then copy back. And so now that I've discussed all of this, let's talk about the CUDA implementation of this code. Now, when you're running a CUDA implementation, you don't need the standard library because you're not allocating any memory on the host without CUDA. So you only need to import the standard I/O header. After that, you can define your size, which in this case I'm also defining again as 1 million. Now, after that, there are a few changes in how you actually declare the functions that will do the addition, multiplication, division, and subtraction. Now, the first change that you can probably see is that there is a global defined in the beginning of all of these functions. What this means is that it'll tell the CUDA C language that this is a function that can be called from either device or host. After that, we're just, of course, telling it that this will return a void, that's default. And then of course I'm also putting a kernel underscore before the matrix add, matrix multiply, matrix divide, and matrix subtract. This doesn't have any language meaning. It's just that, of course, it's a little bit more clean, and you can, this is really just the terminology that we're using with CUDA, kernel. If you don't exactly know what that means, well, I'd really recommend that you watch my previous CUDA tutorial, which will introduce you to all the basics, terminology, drawbacks, and benefits of CUDA before continuing to watch this video. After that, you can go ahead and declare the input that this function takes. Now, as you can see, this function will take input 1, input 2, and output as the inputs to the function, the parameters or the arguments into the function. These are all float arrays. However, you will notice that I'm no longer taking an index integer. Why is that? Well, it's quite simple. Because now, instead of running, for example, matrix add 1 million individual times, I only call the function once. And CUDA will automatically run it those millions of times for me. I just need to specify how to run it millions of times. From there, CUDA will automatically give this function a few different variables like block index, block dimensions, and thread index. From there, you can calculate the index by using those variables that CUDA gives you. Once you calculate the index, then you can actually calculate what the user needs you to calculate, which in this case is the output indexeth element is equal to input 1 and input 2's sum of their indexeth element. From there, I do the same thing for the matrix multiply, matrix divide, and matrix subtract functions, except instead of using addition, I use multiplication, division, and subtraction. But after that, there are a lot of other changes in how you actually call those functions. So let's talk about that. The first change that you can probably notice is that we're not running the malloc function anymore. Of course, we're not running memory alloc because if you watched my earlier video, you know that running malloc will actually give you pageable memory. And pageable memory is not very efficient for CUDA memory transfers. And this is because, of course, pageable memory may be swap memory, it may be given less priority in transfer times, and just generally pageable memory is much slower than pinned memory. With pageable memory, you might be getting 4 to 6 gigabytes per second, whereas with pin memory, you might be getting 11 or 12 gigabytes per second with these sorts of transfers. And so in order to allocate this pinned memory, what I do is I run CUDA host alloc, and this will make the CUDA library allocate memory on the host instead of using a host function to allocate memory on the host for you. In essence, I pass a pointer to in1, into, and out. I tell it the size of these variables, in this case the size constant, times the size of the float data type, and then I pass it the CUDA host alloc default enumerator. Essentially, this will tell it that we're just doing a default host alloc. After that, what I do is I initialize these variables in1, into, and out by setting, of course, as you saw in the last CPU, in1's ith element to I, in2's ith element to I, and out's ith element to 0. After that, what I do is I declare 3 more floats, and these are d underscore in1, into, and out. Now, what does the d underscore mean? Well, d underscore stands for device underscore. Now, what this means is that these are the variables that will be stored in your device or GPU memory instead of your CPU memory. The way you do this is by, instead of running CUDA host alloc, this time you'll run CUDA malloc. This will run the memory allocation function of CUDA, and this will allow you to allocate memory on your GPU. You'll pass it a pointer to the device in1, into, and out, and you'll pass it the size of these variables, in this case, the size constant times the size of the float data type for each. And after that, you will actually copy the in1 from the host to the in1 to the device, and similarly for in2 and out. Now, the way you do this is by running the CUDA memcopy function. You pass it the variable in which you want to copy, and then the variable from where you want to copy. You then pass it the size of the transfer, and you pass it from where to where you're copying. In this case, we're doing CUDA memcopy host to device, since we're copying from CPU to GPU memory. After that, I run the kernel matrix multiply. And over here, we've got a little bit of logic that'll tell CUDA how exactly it should run these functions, or run this function. Now, essentially what this means is that we're taking the size, in which case is 1 million, and we're telling CUDA how many blocks there should be. Now, a block is essentially a block of threads. Now, do remember that the GPU that I'm using, the GTX 1070, can only run 1024 consecutive threads in one block, at least. Not on the chip, on a block. And so what you have to do is calculate how many blocks you'll have to use. Now, in this case, you have 1 million of these, you have 1 million individual, a 1 million size, meaning 1 million elements, meaning that you want to run this function a million times. Now, you can only have 1024 threads in a block, and each thread will handle one individual element. So now what you need to do is divide this by 1024, and that's how many blocks you'll use. But then there's a problem. What's the problem? Well, let's just say that you have less than 1024 elements, say 300 elements. Then you don't even have one single block. So you need to take all of these and add one block to it. And similarly, if you have over 1024 then, that doesn't really matter. CUDA will just ignore that extra block. And of course, the number of threads that you're using are 1024. So you calculate the number of blocks and then tell it that you have 1024 threads. Now, after that, you pass it the device variables for in1, in2, and out. Finally, once that's done, now this is going to be run synchronously, it's not like you just started a task and then it'll return to you. It'll automatically wait, and once all of it is done executing, and this is really the best part about CUDA, it's not asynchronous unless you want it to be. You could tell it to happen asynchronously. However, it becomes a lot easier to program in a circumstance like this, where I want it to act like a CPU function or a sequential function, whereas everything that's parallel is handled in the back end and is actually happening. But once that's done, I then run CUDA memcopy, and I actually copy into the host out variable from the device out variable. I give it the size, and I tell it that I'm copying from device memory to host memory. Because remember, the output of this function was given in device memory. I now need to copy that from device memory over to host memory, and then in host memory, I can do whatever else I want to with it. And from here, it's as if nothing ever happened with the GPU. It's as if we just had those results just like the CPU gave it to us. We can use it just like we would any other result. From there, you can print out the first 10 results using the exact same logic that you did last time. I'm now going to exit out of the editor and run NVCC, the NVIDIA CUDA Compiler. I'm going to pass it my CUDA file, and I'm going to tell it that I want to run. You can specify an architecture though. For example, if I were to run, you can see for some reason it'll automatically use older architectures. And so in theory, I can actually specify it to use newer architectures. Oops. And it uses a newer architecture. The warning is not given to me because this one's not deprecated. This is the latest architecture compatible, the Compute 6.1 architecture, and I can of course also, apart from this SM, I can also use the Compute architecture. They both work perfectly, and as you can see, we again get the correct results because of course 0 times 0, 1 times 1, 2 times 2, 3 times 3, 4 times 4, etc., 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 all the way to 9 times 9, and as you can see, all all of these results are correct, which again, a GPU isn't even not that precise. It is more than precise enough to actually give us these results correctly. And as you can see, we have run all these 1 million multiplication problems in parallel. Now, of course, though, if you're looking to get an advantage while using a GPU over a CPU, you definitely want many, many more operations to be run in parallel because, of course, we're copying megabytes to gigabytes of information to and from the CPU and GPU. And so you need enough of those operations to balance out the disadvantages that the GPU gives you, the drawbacks, the bottlenecks. You need to balance those out. And of course, running more and more things in parallel will definitely help you do that. Okay, so that's what I had to go over in this video today, how you can actually take CPU code that allows you to do arithmetic on arrays and actually go ahead and convert that to GPU code in CUDA. I really do hope you enjoyed today. Thank you very much for joining in. Of course, if you liked the video, please do make sure to leave a like down below. And of course, if you think this could help anybody else you know, like your friends or family, please do consider sharing the video as well. Of course, though, apart from that, if you have any more questions, suggestions, or feedback, please do make sure to leave it down in the comment section below. You can also email that to me at tadgymani@gmail.com or leave it down as a comment in the comments section below, or even tweet it to me at tadgymani. That's going to be it for this video today. Thank you very much for joining in. If you'd like to subscribe to my channel, if you really do like my content and you want to see more of it, please do. And of course, if you'd like to turn on notifications, please do as well. If you'd like to be notified of any more of my future content right as I release it over email and YouTube notification. So thank you very much for joining in today. Stay tuned for the next part of the CUDA series, and of course soon I will also be starting an entirely new C and C++ series talking about all of these C basics in the first place. Thank you very much. Goodbye.